We've developed units as a means of communicating our measurements to other scientists in a way that will be comprehensible to them so they can compare what they get in their experiments to what we got. But there's another limitation that we're always going to encounter, and this limitation is called error. It's the difference between the measured value and the true value. Now, for example, Machine and D'Alembert, when they were calculating the distance between the North Pole and the equator, actually, it turns out that Machine's estimates were a little bit off. He kept coming up 2 millimeters short. Now, he fretted and he went through the calculations again and again. He could never correct this error. He and D'Alembert wound up not telling anyone because they knew that if there was this ambiguity about the number, that they would not have a standard meter. So they hid all of their evidence. But Machine kept trying to figure out where that error was coming from, and he locked himself up in his tower, and he got sick and he died. And this was all because of his meter being 2 millimeters too short. So where did that come from? Well, the Earth is not a perfect sphere. It's a little bit flat up top. There's also continental bulging, etc., which meant that their calculations were inherently off because they didn't match the reality they were trying to model. Now, this is always going to be true in our experiment. There's always going to be some deficiency. All right, there are two major types of error that we have to concern ourselves with. The first is systematic error. So this is a consistent error, which is due to our measuring instrument or method. An example of this would be if I gave you a meter stick in which I had cut off the first centimeter and you didn't realize it. Then if you measured the width of a road and found it to be 50 meter sticks long, well, that wouldn't actually be 50 meters. But the good news about systematic error is it's something that you can fix mathematically. You would realize that each of those meter sticks that you had measured out was 1 centimeter short. And so if it was 50 meter sticks long, then the true length would be 49.5 meters. So you didn't have to go back and remeasure anything. All you had to do was do a little bit of calculation. As long as you know. The other type of error is random error. This is due to fluctuations in the measuring instrument or the environment. So if our meter stick is fluctuating now, 1 centimeter in length, sometimes it's 1.99 meters, sometimes it's 2.01 meters, and this is happening randomly, then we never know when we measure something with our meter stick, whether it was 1.99 meters, whether it was 2.01 meters, or whether it was something in between. Well, it turns out that reality actually is fluctuating. If you zoom in all the way to the quantum scale of reality, the particles that make up our universe are oscillating, and they don't have definite values that we're trying to measure frequently. So this is just a fact of life. We're never going to get rid of random error in our experiments. But we can make some improvements to our experiments to try and minimize this error. As an example, let's say that we are trying to measure the length of a stick. Now, there's already some ambiguity because it's not a perfect rectangle, so where are we actually measuring it from on either end? The stick could be changing in length because it's changing in temperature. Maybe sometimes it's out in the sun, sometimes it's not, so it elongates when it's warmer. Same problem for our ruler, could be changing length depending on the temperature, maybe other factors. The lenses in our eyes could also be changing their focal point because of the changes in temperature. And who knows what sort of mental processing our brain is doing in order to figure out which line this matches up with. It might be that we get different answers depending on whether or not we're hungry. So there are lots of different factors affecting what we're actually going to measure for the length of the stick. And what we will do is we will go ahead and start performing some of these measurements. As we measure the length of the stick once, and it looks like it is 4.99 centimeters in length. We measure it again, and it seems like it is 4.98. One time we measure it, it's 5.03. In general, we tend to measure values close to the center. And as we continue to perform all these measurements, we get something that looks like this. This is called a bell curve or a normal curve. So it's a distribution where we have a lot of measurements clustering around some central value. And then there are a few measurements way out here called the outliers. So what we tend to do is we tend to assume that this central value is the actual length of the stick. So this is going to be our true value. But there's an issue here. Our issue is that what if, since these are completely random measurements, what if we measured a few more random measurements over on this side? What that would do is that would tend to weight the left side more and shift this quote-unquote true value over to the left. Or what if we had gotten an excess of measurements over here on the right? That would tend to shift that true value over to the right. So we can't know for certain that this central value we calculate from the curve is the actual length of the stick. What we tend to do instead is we tend to bound off about 2/3 of these data points and say, well, we don't know the exact length of the stick, but we are pretty darn sure that its exact length lies somewhere within this width here. And so we would say the length of the stick is 5.00 centimeters plus or minus 0.02 centimeters. Let's introduce some terminology now. In order to describe our error, we talk about accuracy. This is how close we are to predicting the true value. Imagine that we are measuring experimentally something that we already know, like the value of pi. So we're taking out our rulers and we're measuring the circumference and diameter of a circle to calculate pi. We know its true value is 3.1415, etc. But our values from our experiment all seem to cluster around this central point over here. So the difference between those values is a measure of our accuracy. Of course, if this distance is larger, then our measurement is more inaccurate. This tends to correspond to systematic error. All of our values have been shifted over by this certain quantity. And so if we know the origin of that shift and its value, then we can just subtract and correct our curve so that it centers around the true value. We also have precision. This is how consistently we measure the same value. That corresponds to the width of this curve. If we're very precise, then the data points will tend to cluster tightly around the central value. They'll tend to be within the range, say, of 4.999 centimeters to 5.001 centimeters. And we will have very few out in the value range of, say, 5.02 centimeters and 4.98 centimeters. But that doesn't, just because it's precise, doesn't mean that it's accurate. In this case, we are measuring a very precise value that happens to be incorrect. It's not this true value over here. Because error is going to be intrinsic to every measurement we ever perform, we want to have a means of communicating the error just as well as we want to be able to communicate what we think the measured value is. So how are we going to do that? Well, first of all, we're not going to worry so much about the accuracy, because if we have insight into what the true value is, we're probably going to go ahead and use that better value. What's going to matter is when we are trying to infer the true value from that normal distribution. And so in that case, what we are worried about is the precision. Now we're going to need some notation for precision. There are a few options for this notation. The first way that we could represent the precision of a number, let's say that we measure a value of 1.0047, and 2/3 of the data points tend to cluster within the range of plus or minus 0.0093. So this 0.0093, this represents our error for this measurement. And we could also write this in more compact notation. We write 1.0047, and then in parentheses we write 93. And so you start counting over from the right side of the digits. So the error in that 10,000ths position corresponds to the 3 that we've written in parentheses. And then the next digit is the 4 in the thousandths position. So there's an error of 9 in that thousandths position. A final way of indicating this error, we have what is called significant figure notation. And so in this notation, since we have significant error in these last 2 digits, what we're going to do is we're simply going to omit to write those digits, and it's going to be implied that there is significant error for whatever digits that we fail to write. There are some additional rules for representing significant figures. First rule, if we have zeros in front of the number called leading zeros, then those do not count as significant figures. So here in this number, we only have 3 significant figures. This is also true with decimals. So 0.00487. We again only have 3 significant figures. And this makes sense, especially if you consider scientific notation, because the first one would be 4.87 times 10 to the 2, and the second one would be 4.87 times 10 to the minus 3. And I think it's evident that both of those numbers should have the same quantity of significant digits associated with them. However, if you have trailing zeros, then these often are significant. So if I write 1.00, then this is meant to indicate that the 1 is significant and these other 2 zeros are significant. If they weren't significant, we wouldn't bother writing them. But if you have a number like 100, now it's not quite clear whether or not these zeros are present simply so that that 1 will occur in the hundredths position, or if they're present because we actually measured 100 as a value. In order to make this more evident, we will often either write overlines to show those zeros are significant, or we might write an underline to indicate the last significant digit. Another method, if 100 is significant in these first 3 places, explicitly including the decimal place, indicates that that is so. So this has 3 significant figures, this has 3 significant figures, this has 3 significant figures because it's significant to this last 0, and this also has 3 significant figures. Finally, remember that we're using this notation to indicate precision. And precision only comes in when we actually measure numbers, when we perform experiments, because that's where we have limited precision. If we have something that's computational, such as the number pi, that's equal to 3.141592658979, etc., etc., etc. Well, this is an exact number. We could carry this out to infinitely many decimal places. Or if I say that I have 2 apples, that's again an exact number. I do not mean that I have 2 and a fraction apples, or I might have some uncertainty there. This is a conceptual quantity. So it has infinite precision associated with it. We're probably going to encounter situations where we have to manipulate in some way these numbers that we've written. And so how are we going to account for our limited precision in the final results? The basic idea is that we only want to keep track of the largest portion of the error. You imagine that you're trying to measure the length of a road, and you can measure the starting position really precisely because you're standing right there. So you know it to about plus or minus a couple of centimeters. But the final position, you're not quite sure about. Maybe you have kind of a hazy picture in your head of the place that you're going to. But you can isolate it to about 1 kilometer where this place is. Well, in the final estimate, you aren't going to worry about the 2 centimeters any more than if you were trying to tell your friend it's about 10 miles to the corner store. Not going to account for your uncertainty in the width of your doorway as far as getting there, because that's going to be irrelevant compared to this much larger uncertainty. And that's what we're trying to represent in our notation. So first of all, let's consider the case where we're adding and subtracting numbers. Our rule is going to be that the largest final decimal position from our input numbers, so that's everything that we're adding and subtracting together, is going to be what determines the last decimal position of our output numbers. So for instance, let's say that we have 0.2456, and we add 8.913, and we add 1.1. All right, so this 6 is in the 10,000ths position. This 3 is in the thousandths position. And this decimal is in the tenths position. Well, a tenth is much larger than a thousandths or a 10,000ths. So this is going to be the one that determines our final decimal place for our answer. So we calculate our answer, and it comes out to 10.3, and we'll stop right there in the tens position. You might also be doing multiplication or division. In this case, our rule is that the least quantity of significant figures of our input numbers, what we're multiplying and dividing, is going to determine the final quantity of sig figs of our output number. So consider that we have, say, 100.1 times 22.8. So here we have 4 significant figures. Here we have 3 significant figures. What that means is that our final answer is going to have the lesser of these. It's going to have 3 significant figures. So we'll write this as 2,280. And it's probably a good idea if we maybe do something like put a bar over this. And that's telling the person who reads this that the 2, and the 8 are significant. And this final 0, which remember can be ambiguous, is not one of those significant digits. Now let me just prove to you why that this rule is true. Let's say that I had 10.01 times 7.0. So my significant figure notation is saying that this next digit, we don't know anything about it, could essentially be anything between 0 and 9. Let's say that it's 0. In that case, our answer comes out to 70.07. It's about equal to 70. Let's check the other extreme. So that erroneous digit, which we don't know what it is, could be anything. Let's say that it's 9. We calculate this, our answer comes out to 70.97, which is about equal to 71. So 2 significant figures here, 4 significant figures here. You can see that our answer varies in this second significant figure. Everything after that is garbage because we range between a value of 70 and a value of 71. And so there could be 9s, 8s, 7s, 0s, etc. Anything else in those further decimal places is still going to be within the range between 70 and 71. So we're clearly correct in choosing 2 significant figures, since the variation all occurs in the second figure, and after that it's garbage. And if you're ever wondering what a new significant figure rule should be for some complicated mathematical operation, you can do this. You can figure out what those erroneous digits are and put in the smallest value, put in the largest possible value, and see which decimal place is changing in your final result, and you know that that's your last significant digit. Let's try a more complicated example. So I've written this expression here. We'll do our best to resolve it down to a single number using our significant figure rules. First of all, we have to be wary of orders of operations. So there's parentheses here around this quantity. So that means we're going to do that first. And then we do multiplications and divisions before we do additions and subtractions. Let's go ahead and start over on the left side. So 141.2 goes to the tenths position. 5.01, that goes to the hundredths position. Our rule for addition and subtraction is that whatever decimal place is the largest among the numbers that we're adding and subtracting, that's also going to be the decimal place that we use to terminate our answer. So tenths are larger than hundredths. So we add this together, get 146.21, and we're going to stop in the tenths position. So our answer is 146.2. Now we're going to divide by e. E is a mathematical constant equal to 2.71828, etc. Now recall, whenever we have constants, whenever we have anything that's not a measured number, they have infinite precision. All of these digits are significant. So our rule for additions, for multiplication and division, is that we go by the least number of significant figures. Compare 4 to infinity. I think it's clear that 4 is the smaller quantity. So we want to have 4 significant figures in our answer. I punch this into the calculator, get 53.787, etc. And we're only going to carry this out to 4 significant figures. So that will be 53.79. All right, let's start on the other side. We have 12 eggs divided by a dozen eggs times 4.81 times 15.006. So all multiplications and divisions, which means we go by the least number of significant figures. Here we have 3 significant figures. Here we have 5 significant figures. What about 12 eggs for a dozen eggs? Well, that's not a measured number. That's a definition. There are 12 eggs in a dozen eggs. So because that's not measured, that means that this has infinite precision. So the smallest amount of precision is this 4.81. has 3 significant digits to it. So multiply out 12 times 4.81 times 15.06 divided by 1, and you get 866.14637, and we only want to have 3 significant figures in our answer here. So this is 866. Our final step, we need to add these together. 53.79 plus 866. Back to our addition and subtraction rules, which means we look here, we have a hundredths place. Here we have the ones place. Well, 1 is definitely greater than 1/100th. So our answer is going to go out to the ones place. That means that our result is going to be 920. And this last digit is significant. So we might indicate that by putting a decimal place there, or by writing a line over it. What if you're collecting data yourself? How do you know how many significant figures you should use? It's really easy if you have a digital instrument, because then you just read to the last digit which was displayed. And these instruments will always be designed to read that far, because that's as far as the instrument's giving useful information. They wouldn't bother putting in a digit after that, which is just going to be some random number between 0 and 9. That would just be more expensive and wouldn't help you. Now, for analog instruments, if it's graduated, so it has little division markers like this ruler here, then what you're going to do is you're going to estimate to 1/10 of a division. So let's see. So here, the length of the stick, we have 4 centimeters, and then we have 5 millimeters. It looks like maybe this goes to, say, another 0.5 millimeter. So I would estimate this as 4.55 centimeters. There's going to be some error in this last 5 here, this last digit, but it probably still conveys at least some useful information. You're going to be able to tell the difference between 4.50 and 4.59, even if you can't tell the difference between 4.51 and 4.52. So including that last digit helps to add in a little bit of extra information that you actually do have available to you. Now, if you don't have gradations, then probably you're just going to be looking up the value. Many pieces of equipment, like volumetric flasks, have defined error depending whether it's Class A, Class B, grade laboratory labware. And otherwise, you can probably find it from your manufacturer. Finally, just give you some expressions for determining total amount of error. Usually use these once you've reached the end of your experiment to see how accurate you were. First of all, we have percent error. So you take the difference of your approximate value or your experimental value minus your exact value, or the theoretical value that you predicted you were going to get before you performed your experiment. And you take the ratio to the exact value and multiply by 100 to turn it into a percentage. You will sometimes, actually you'll quite often see absolute value signs around this expression. The reason for that is because of our binomial normal distribution here. So because it's symmetric, if we have a positive error, that also implies a negative error, because we're saying that we have the central value that we're giving you and that the error is within this range. So we often just take the positive quantity to tell you the magnitude of the displacement there. We also have percent yield. So this usually tells us the difference between how much of a chemical substance we got versus how much we could have got if everything went perfectly. So that's your experimental value divided by your theoretical predicted value times 100. And we could also simply compare two quantities. It's the percent difference. So you take the difference of the two quantities and then divide by their average, which is just their sum over divided by 2, and then again multiply by 100 to make it a percentage.